Hello, starting a class of iPlant. So last week we have done to analyze the synteny, the phenomena of synteny between two different species. So the two different species has diverged into independent species. Maybe not that independent, but we will tell it independent species. But along with its own evolutionary path, they conserve the gene orders. So that is we call synteny, or sometimes we call it gene collinearity. So when we talk about the homologue between two species, we can just merely blast it, and the top hit can be considered as a homologue. But in addition to that, if we apply the synteny phenomena, then we can more logically extract the direct homologue rather than just merely do blast. So that's why we are studying how retrieve the synteny between two species. So last week we selected one software that was MC Scan. So MC Scan is that MC Scan is one software from this homepage, right? So we downloaded and we tested the software with our local right. So we have tested the MC scan in our local environment, iPlant, and that was in the blast, right? Yes. So MC scan X, we tested the example data. The example data possess this blast result. So this blast result can be extracted from our blast result. But this is the example data, so the authors already built in the data folder. And the collinearity is coming out of the MC scan software. So we run the software and get this file. So let's do it again with this one, and so MC scan X is result. MC scan X, and just type this one. Okay, so you are typing OS underbar SB, but this software automatically recognize these two files, blast result and simplified GFF, and it will calculate the collinearity based on the homology and the genomic location. So it will calculate it so quickly. So quickly, and it will gives you the result. So there was no collinearity file between OS and SB, but you will see now there is collinearity. In addition to it, there is some folder is created. So let's check this file. Then it will give you a synteny block. 0, 1, 2, 3, 4. Many synteny block can be observed. So this synteny is between Oraida sativa and Oraida sativa itself. But in this case, this synteny number 45, is about between OS and SB. So this must be the bicolor. So what? Setaria bicolor, right? Setaria bicolor and Oraida sativa. So it has some synteny. And if you are interested in the visualization, then you can go to the further and data and HTML, and you will see the result. So it gives you the situation. So this situation. So this is the gene order of Setaria bicolor, and this is the gene order of the Oraida sativa. So this one is omit in Oraida sativa, but this one and this one is conserved in Oraida sativa. So you can see some is gone, but the other is very well conserved. This is direct evidence that there is kind of common ancestor of gene order. Some gene order is common ancestor. We do not know. So maybe this is true, maybe that is true, or kind of the summation of these two order will be common ancestor. But we can be sure that there is some common ancestor. From that common ancestor, this Setaria bicolor is came out, and this Oraida sativa came out. And these two has common phenotypic appearance. But as you know, the grains are completely different. Right? So this is our main food, and this is not our main food. This cannot be. And also you can see this phenomena. So one synteny block, so synteny block number 4, have four different synthenies. So synteny block is conserved in 4 different ways. This is not good example, but maybe this is very good example that we can talk about some whole genome duplication. So many times within their history, so I mean the history of the Oraida sativa and Setaria bicolor, they have many times of duplication, whole genome duplication. So whole genome duplication means that the genome compound has copied. So whole genome had been copied. Why? We have no idea yet, but there is so many papers coming out about whole genome duplication. Genome duplication. So whole genome duplication. There's so many whole genome duplication papers. So only this topic can be paper. So significance of whole genome duplication on emergence of evolutionary novelty. I don't know what that means, but they are reviewing the relationship between whole genome duplication and acquisition as evolution, right? So they means that maybe this whole genome duplication is kind of very important driving force for the evolution. So that is true actually. But horizontal duplication not happen that frequently. So maybe there is yes. So this is I don't know what paper is, but let me check. So I don't know. But this is KS value. Yes, KS value. So these KS distribution actually indicate the event of the horizontal duplication. So the meaning is that KS value, so this value is, happening a lot. This value happening a lot, and this value happening a lot. Why these values are happening that a lot? Because there was horizontal duplication at that time. So meaning that KS value can be translated into the time. So if you have small KS value, then your horizontal duplication time will be very recent, and this is not recent compared to this. This is must be very ancient. So this is how we translate this KS value. Then what is KS value suddenly? So KS value is coming from synteny. Okay, so synteny Doppler and KS correlation is yeah. So there is not enough documentation, but we already know that this one, downstream analysis has add Ka and Ks to collinearity. So they have already the software. Okay. So let me check how can we run this file. So command are not found. So per, do we have per? Yes, we have per. And okay, can locate. So this means that we have to install BioPer. Let me check if I can install BioPer with Conda. Yes, there is. Thank you. So Perl compared to Python, so Perl was best bioinformatics tool, language. However, now it is, yes, still yes, but Python is better, I would say. But still, there are so many Perl application, which is really good, especially this one, MCScanX. Then we have to know how to install. So what is necessary? So BioPerl is necessary, and how to install this BioPerl in your computer. So this is very important. So when I was studying bioinformatics, installing BioPerl is like a hell, or was really difficult. But hopefully this Conda would install BioPerl safely without any errors. So if you encounter certain error, it is really hard to fix it because the complicated dependency is the problem. Sometimes it cannot be solved. then you have to erase everything and you have to open it up again, or you have to format the Linux and restart it. So that was really big problem. But nowadays the other solution is there, which is called Docker. Okay, so Docker actually gives you virtual environment which can be easily created and deleted and restarted. So then you don't need to erase everything or format everything. Just open new Docker and install. So BioPerl installed. So BioPerl, and let me run this one. Go. Okay, it gave me clear uses, which means it run safely. Okay, so it says colinearity file and CDS file and output file. We have colinearity file, but we don't have a CDS file. Let me check. Data. No? So ATCDS is there, but there is no BTs. Disappointed. Okay. So only Arabidopsis is there. So let me check. Let me check. So GS something. I don't know which version is it. So that must be protein sequences. So somebody opened their server. Species. BTs. And download coding sequences. Thank you. Let's wait. So what I'm doing is here. I'm blasting the Hibia brasilensis. What was that? The laboratory and Arabidopsis to have the collinearity file. So first of all, what we have to do is blast, but it takes a lot of time. So I put this file to our server. So this is our server. So our server actually working a lot to retrieve the blast output. So having blast output, then we can run the what was that? mscanx for getting what was that? collinearity, right? So that's a hard-working server that was ours. Okay. So somebody made some tools. Compare profiles. What kind of comparison can be done? Use these tools simultaneously to display the expression profile of multiple genes of interest. Okay, load example. Show the profile. Oh, good, good. But this is not cool because this is just one observation. So this cannot be generalized. So at least they have to collect many samples. And this visualization is not so effective comparing different genes. But making this kind of database is really good. But the problem is the way you showing the database. Download, then it will gives you this table. This is good. Tool, what kind of other tool you have? Custom network, show the co-expression. Okay, load example. Draw network. Okay, this is not good. So this is kind of good idea to give people to have a certain network. However, this is too messy. All right. Anyway. Okay, this is done. This is done. And I will copy this file. I will copy that file to C drive of Ubuntu iPlant blast msyskinx here. Okay. Good. Okay, then let me check the file. Where was the file? I think I have to move here. Okay. So BB. Good. So let me check exactly this is the right form or not. T BB. So we have to check it here. Good. Then we have to merge. We have to merge this coding sequences into ATBBCDS. Then you have new CDS file and part downstream analysis. Add and input was collinearity and database is CDS. The output is, and I will say KAKS. So run. This is really good software. Okay, so it actually we try. I mean, take advantage from the another software cluster X, no cluster W, and it automatically calculate the coding sequences alignment using that software, and it drive the synonymous and non-synonymous variation, and they calculate Ka and Ks. So I forgot to explain you what is Ka and Ks. Very important statistics when you talk about the evolution. So in genetics, the Ka and Ks ratio, also known as this one, how do you call this one? I don't know. Omega. So this was omega. Okay. Omega or the NDS ratio. So was used to estimate the balance between neutral mutation and purifying selection and so on. But the Ka is the ratio of the number of non-synonymous substitution per non-synonymous site in given period of time. And Ks is the number of synonymous substitution per synonymous site in the same period. So must be some examples. No. No. So actually, mathematically, it cannot be from me explained, but I can tell you the simple scheme. This use non-synonymous site. What is the synonymous site? Synonymous site is SMP, but protein doesn't change. Okay, SMP, but the protein doesn't change is synonymous site. But non-synonymous site is protein also change. So that is the non-synonymous site. So based on the non-synonymous site, and it calculates the number of non-synonymous substitution. So this is alignment. So this is alignment. So it will calculate. I think there is some visualization. So you can see the this is SMP, but the protein doesn't change, right? Let me go to this one. So this slide share will tell us. So thank you, Manos. Thank you, Manos. So let's go to the synonymous site. Okay. So there is kind of selections. The hypothesis, negative selection, will be similar with the meaning purifying selection. So selective removal of deleterious mutation, positive selection, adaptive selection, Darwinian selection, increase the frequency of beneficial mutation. So this is removal of deleterious mutation, but this is about beneficial mutation. Okay. So move on. So purifying selection is that synonymous substitution is 6. Non-synonymous substitution is 0. So in this case, right? So there is so many SMP. However, there is no change in a protein. So number of synonymous substitution is 6 and non-synonymous substitution is 0. So Ka divided by Ks will be 0. So this is a kind of radical case of purifying selection. So neutral selection, it will be some site is synonymous, some site is non-synonymous. So 3 and 3, and it will give us 1. So this means that neutral selection. So then we can quantitatively calculate between 0 and 1. So this is how we are talking about purified selection and neutral selection. But in this case, the Ks, the synonymous substitution, considered not affecting the protein function, right? So even though it has SMP, but the protein sequence is same, so we are thinking that there is no functional change, okay? So which means these variation don't don't be affected by time. What is the meaning? Don't be affected the time. Why? The phenotype is same. If there is some kind of phenotypic changes, then it will affected by time. Why? The time has the environment. So environmental changes is the time, right? So environmental changes will suppress or promote certain mutation of protein, right? But there is no changes in protein. So these SMP, nucleotide SMP, will not be affected by time or environment. So without time, there is no environment, right? So we can calculate the time based on the Ks. So that is the meaning of why we are saying, where was it? Did I miss the? So this is also the other figure that has Ks. So Ks will be considered as time. So why there is peak? Why there is peak in certain Ks value, which means there is some kind of explosion of copy. Okay. So at that time, a lot of copy happened. So there is so many density of certain gene pair. So we are consider there's duplication and duplication and duplication, or divergence. This is how we translate the synteny plots. This is also, there's so many paper you can see. So Ks value and this peak is shared, right? So we are considering this is well shared. And Medica Otrum catula and Lotus japonica, Lotus. So they must be this one, and Medicago also this one, right? So Arabidopsis is this one. So these three species has shared whole genome duplication at where? 0.8 or 0.67. Interesting. Here also, striga. What is striga? I don't know. What is striga? Cell. I hate cell. Striga? What is striga? So this is kind of what is the importance? Why they publish? So this is current biology. 최도일, 켄 시라수. Okay. Okay. So I know that 켄 시라수 is famous with this parasitic plant. I heard that he published some kind of parasitic plant in the science. 최도일 교수님. Anyway, so this is not important. Why I opened this? Why I opened? Okay, this. But we have to purchase. No, I will not purchase. Anyway, so this is how we translate the KS. Anyway, so let me check if we have. So this is still calculating. So I hope you guys also try this calculation. Okay. So I told you that how to retrieve the BTS CDS, right? So download the BTS CDS and calculate it like this. Also, I will check the blast. Blast is also going on. And okay, so let me wait until this 2 is finished. So the blast is done. So blast is done. So we are having this one. This one we are having. So I will convert. So I will check. I will check the result. I will check the result. The result is like this. Actually, we used the transcript rather than genes. So this is the reason why we have these numbers, but that is no problem. And we have to change. We have to change the GFF file into different one. So what do we have? I will download the result blast, and I will copy this one to data. No, let's make new one. Blast. So blast we have the files. No, yes. So the blast is go here, and what do we need? We need GFF file. So GFF file. Do we have GFF? I thought we have GFF file here. No, yes. Okay. So we have GFF file. Then okay. Oh, so this is also done. After explaining our laboratory, so I will give you explanation of no. I will give you explanation of the file also. Jupyter Lab. Okay. Okay. So let's check the GFF file. So this is the GFF file. Chromosome, gene name, and position, and position 1 and position 2. So we will recreate the Arabidopsis thaliana 하나 GFF3 47 FF3. So we have it, and let me make transformer or converter in the GFF3 to MC scan GFF. MC scan GFF. I don't know. All right. So import pandas PD. Okay. Import pandas. And data frame GFF pandas read CSV Arabidopsis separation comment ubi shop and header none GFF head. You can open up easily. And what you're gonna use is mRNA, because you already saw that our result is like this. So the name was based on the mRNA. So we will mask data frame GFF to core mRNA, right? And GFF data frame GFF mRNA. Okay, and first of all, you have to use this one, the chromosome, and you will use the name. So let me use the name first. It's 8, 2, no, 2. So how can you, so split, right? And for x in, x split. Okay. This was the one, and dict, and it will become dictionary. And what ID. That's the one. And I don't like the transcript. Place transcript. 뿅뿅. Good. So this what we want is that apply 8. Apply 뿅 and lambda x and it goes to here. Good. But let me use another one. I and I. Good. So we have it. Name. So we have it. And then name. Oh. Oh. So chromosome, name, position, position. Chromosome, name, position, 3 and 4. Good. To CSV. AT, GFF, separation will be tab, header, non, index will be pulse. Good. Yeah. We made. So we made it. And everything. Only this code. Only with this 5 line. Okay. Only with this 5 line, we could make very good MC scan. Okay. But the problem is, I would say it will not be same as Arabidopsis. So I really think that is the problem. Okay, so mRNA we selected safely, and this is the transcript name they are saying. So oh my. Protein. So it has different name of protein. This is problem. So, So XP, it has, and mRNA has XM. So this is different scheme of the expression. I think there is a way to convert them. Let me check it. So NCBI XM to XP. Lipstick. Hopefully there is a way. So wait for a while. Oh, there is a interesting way to using um, the entrance direct the API. So we can extract the protein ID using eSearch. Let me check if we can install Antras Direct. So Antras Direct is something like this. But let me check if Conda have it. And Antras Direct. Sure. Conda rules. No. So this is the first time that I'm using this API. Go. But using API, it takes time because we send our query to their server and server process it and they give us back the answer. So it takes a lot of time for processing many things. But we have a lot of time. All packages are already there. Okay. I didn't know that I had already have it. So let me just run this code. 영. Wow, it takes too much time. Can I just grab the old table rather than having X protein accession, mRNA accession table, NCBI, protein, mRNA ID table, rapsic, submission. I'm pretty sure there is a way. Wait for a while. So I found that. So just we can iterate. We don't need to iterate. So we can send our query in this way. So I think this will be more easy to give them our transcript ID. So let's split first. Split first. So everything is very laborious. I don't want to do this laborious transcript ID. Okay. So data frame. So 몇 번이니? 8번. apply. 보다 I. So instead of having this one, I split. Good. Then this is the name, and we will we have this, and what we are doing is that name, name values for x in um, so 네. Okay, and okay. So and let me check. So this is no. Ugh. This Q. I will put it Q. And our command is this one. Okay. Q. And output. Hopefully. It will, no. Argument is list too long. Sure. So how many do we have? So 1,000. So I want to have 1,000. Lang. Okay. Work. Number of works. Number of works is like this for each in range. Number of works is like this, and out each so each plus 1 에 1000 맞니? 응? Hopefully it will accept the 1,000 query. Hopefully. Temp. So no. So let me just put 2 here. Put plus temp. still it takes time. I hate, but it gives us the result. Okay, then just do it. From and DM and box. 아유. So I think it will take more than 1 hour, no? 10 minutes? 10 minutes will be no problem. Okay, cool. Just for a while, wait. So, it's done. Actually, it's done. So the output gives us the. Let me check the length. Oh my. So I think the length. No. The length of our out should be like this. So which means Enver. So Enver works. So fifth, seventh. So we have to do this one more time. We have to do this one more time. We have to do this. 7, 7. Right? Yes. Yes. Go. Okay. Then output is right. Okay. Then data frame. We had this data frame. The name corrected is output. Right? Then this one would name corrected will go and HB. Now we have it. Okay. So we have it, and then so we are making blast bar, and we are making GFF file 80 HB2 80 GFF. Good. So we have these two. We have these two files HB280 HB280, and we will run mcscanx and HB280. Hopefully it will compute very well. So the laboratory config is so many compared to Arabidopsis. It gives us list of HTML, but we don't care because I can observe Arabidopsis files. Cool. Let's open this folder. I think no. Maybe it has too many files in the folder. So it is not working. So on the other hand, okay, sorry. So let me just go to HB2. So it will give us a lot of HTML, but I will erase the NW, right? So I will remove NW stars HTML because I don't need it. Okay. So we have them. So this is also curious. So there is no collinearity between mitochondria. What about the chloroplast? There is no collinearity. But what about chromosome 1? So there is few collinearity. It's very hard to show in this way. Let me go to the collinearity file. So the block is not so big, but still there is collinearity. This is all. So this is so small. I think this is unusual. What is the distance between lobar tree and lobar tree? No. Hevia brasiliensis. So this is dicot. So I don't think it is so far from Arabidopsis. I think the problem is the contig length is so short. That is the problem, I think. Hold on. Did we download it? The whole genome sequence? Yes. So let me check if the whole genome sequence is so short or not. So Abyss is assembler. So this assembler gives us some very how you say, useful tool to evaluate the assembly. So Abyss spec. So Abyss spec is the software. So we have the this one, right? So this one is the so that this one is the file. So Abyss spec, and then it will calculate the N50s. M50s. Maybe one time I explained what is M50. So what M50 is the kind of a median length, so median point of whole genome sequence, middle point of whole genome sequence, and when you ordered the config based on the length, and you point out in the middle of the whole genome, and you grab the config and measure the length of the config. That is M50. So the longer the M50 is, then your assembly is highly contiguous. So that is the logic. But the problem is laboratory itself heavy brasiliensis genome size. The genome, laboratory genome, that was the paper. So they are also talking about M50 lengths. Okay, so it is 2.15 gigabase. So the assembly spans only half of the genome. So okay, so the coverage is not so good. How can they publish the paper then? Interesting. So M50 of the config of M50 is just 30K. Not good. The scaffold is 1.2 megabase. Then it should have something. Did they? Wow. Anyway. Okay, so let me check the result. The M50 is 1.2 megabase, which is same as the report. And the number of the scaffold is so many. So 7,000 scaffold is there to cover whole genome. But the problem is the skin genome size is 2.15 as estimated genome size, but the sum is just 1.2 giga. So they do not cover everything, even though they have this number of M50. So that's why our synteny is so small, I think. So the reason, actually they have a lot of sequences that is highly repetitive in a tree genome. So with this length, maybe it is very hard to calculate the collinearity, which means between these two genes, there are so many repeat regions. So this is compact, Arabidopsis compact genome, but this is very, let's say, extended. No, so it has a lot of repeat anyway between two genes. So like a sea of repeat, very broad and large sea of lipid, and the genes is floating around, uh, and it has large gap between the genes. But Arabidopsis is very compact. That's why it gives us this small number of synteny. And okay, so bit late, but we recognize laboratory genome is not that perfect unexpectedly. So I was thinking that it is very published in a Nature plant. So I was thinking that they had very good genome, but it was not. Anyway, this is how we calculate the collinearity, and let's see the result of the KAKS, this one. So we calculated, and this is similar with previous result, but you may recognize this means KA and this means KS. Maybe yes. And it gives us all KA and KS value for these two pair. I mean this pair. So you can calculate the distribution of K and KS, or you can calculate the selection type of selection on this gene pair by Ka divided by Ks. So we will do that next week. And so, okay, this is it for today. Thank you very much.